Okay, please confirm, one or two of you, please confirm that you can see the presentation
Yes, sir.
as well as hear me. Okay, fine. Thank you very much. Please mute the mic, all of you, and then we shall start. So, here we are. Let's see. Um, this is the subject that we ended on in the last class. This is about finding phase plots of first order autonomous systems. It gives you a very simple, I mean, I would advise you to follow the discussion closely, because this will give you a very simple a bag of very simple mathematical tools, with the help of which you can solve many apparently complicated physical problems. By physical problems, I mean the problems of physics that we have considered so far, or are to consider in the future. So this is a mathematical discussion, of course. There is no physics over here, but this discussion will be helpful in making simple approaches to many seemingly complicated or difficult problems. In the classes so far, we have been discussing autonomous systems in various physical contexts. Particularly, we ended with the context of in the on the context of particles falling through, or objects falling through long fluid columns, such as a liquid column or air column. The next problem that we shall take up is the problem of a bicycle rider pushing against air resistance flat on the flat horizontal ground. So these methods, these mathematical methods that I'm about to take up now, will be helpful in this particular problem, and probably several others later. So let us see how we go about this business. We'll talk about phase plots of first order autonomous systems. The word phase plot, the term phase plot, actually refers to plotting position and velocity. So here it is something like that almost. If x is position, let us say distance, then dx dt is velocity. So basically, we are solving a plotting x dot, which is like velocity, although I would rather not stress upon too many physical contexts at this point, because I would like to keep this discussion mathematically general. Mathematics is a far broader field. We just use a part of mathematics to understand certain physical problems. That is what it is. So x dot is like your velocity, dx dt, and x is position. So we are plotting. So if you are given an autonomous function, first order ordinary autonomous differential equation, and if you are given a system like that, so it is like x dot is a function of x. So instead of plotting x as a function of t by carrying out an integration, what can you conclude by an even simpler approach? Instead of integration is not always very easy to do. So even without integration, can you derive some meaningful conclusions from the autonomous system that you have in front of you? Let us see. So here we are plotting x dot as a function of x, and the simple function that we begin with is a minus bx, which is a linear function. So you plot x dot along the vertical axis, x along the horizontal axis. These were the things we discussed in the last class. This is if a and b are both positive quantities, then this is the resulting straight line. Now comes some useful things. What is x dot? X dot is like the rate at which x is increasing, changing with respect to time. If x dot is positive, and how will you say x dot is positive? If anything, if the function is above this horizontal, this is the horizontal line, this is the x-axis, and this is the x dot axis. So if the function is above this horizontal line, then x dot is positive. If x dot is positive, then x must be increasing. So you start at some value of x, let us say x subscript 0, x naught. Thereafter, if x is increasing, then you can only go in the increasing direction of x. So you draw an arrow going from left to right, which is the increasing direction of x. Then here is a point where towards which this arrow is pointing. Then as you cross this black dot represented by this point and go to the other side, then the function line, this straight line falls below the horizontal axis. If it falls below the horizontal axis, then x dot is now negative in this region. If it is negative in this region, it means that x is decreasing with respect to time. X dot is negative, right? So if you start at any point over here, then you will turn the arrow going from right to left. The direction of the arrow will be reversed, which means that x is now decreasing. And it is towards this black dot that from both sides the arrows are pointing. That means that this is an attractor. If you start attractor, meaning attractor is something that attracts, and it is a stable attractor. So we shall first of all try to understand the meaning of these words. First of all, there are three phrases here: stable, attractor, and fixed point. Here we have what is called a fixed point. Why are we calling it a fixed point? It's a fixed point because at this point x dot is equal to 0. As soon as this horizontal line crosses this straight line crosses this horizontal axis, x dot is equal to 0 at that point. If x dot is equal to 0, then that point is technically referred to as a fixed point. X is neither increasing nor decreasing at that point, so it's fixed, right? Okay. Next, attractor. What do I mean by attractor? You start with a value of x at this point, you'll be attracted towards this black dot. You start at a value of x somewhere here to the right of the black dot, you'll be attracted by being forced to go to the left. So this is an attractor point, and it is also a stable. Just a minute, please. Hello? Sir, I'll call you back later because I have a class. Thank you, sir. Hello. Yes, I hope you're all able to hear me. So here, this thing is, so I've been able to explain fixed point. Fixed point meaning x dot is equal to 0. X is neither decreasing nor increasing. X is not changing. That's why you call it fixed. Attractor meaning things are attracted towards this point. Stable. Let's now analyze the meaning of the word stable. Consider a simple equilibrium configuration. I have given you a pencil, and I'm asking you to test for the equilibrium configuration of the pencil. Now, there are two equilibria that you can attain here. One is by keeping the pencil flat on its side on the tabletop. That is an equilibrium state. Another equilibrium state is to balance the pencil on its pointed tip and make it vertically stand. That is also an equilibrium. However, there is a major difference between the first equilibrium and the second equilibrium. What is the major difference? That in the first equilibrium, suppose the pencil is lying flat on the tabletop. I ask you to lift the pencil a little, holding up one end, and then release it. What is the most natural thing that you expect to happen, even if you are not doing the experiment? Just try to run over this whole process in your mind. The pencil will fall back again upon the tabletop. So basically, it was lying flat on its side. You lift one end of the pencil slightly, not very much. You lift one end of the pencil slightly and release it. It will again fall back to where it was. So basically, earlier it was in equilibrium, lying flat on its side. You disturb the equilibrium a little by lifting the pencil a little, but as soon as you release the pencil went back to its original equilibrium state. Therefore, this sort of an equilibrium is called a stable equilibrium. It remains stable. What about the other scenario? I have balanced the pencil on its tip, pencil, a stick, or whatever. I've balanced it or at one end and tried to make it stand vertically upright. But if there is a slight breeze, a little push or anything, if you disturb this equilibrium a little, then immediately it will keep going away from that equilibrium and never return to it. Suppose you are making a stick stand on one end. It'll just stand, wobble for a little while, then a little breeze or anything, it'll just fall flat on the ground. So the second kind of an equilibrium it may be, but it is an unstable equilibrium. Unstable as in that if you create a little disturbance to the equilibrium state, the equilibrium state will not be restored. It will keep going far away from the equilibrium state. So basically, this is like that first scenario where something is in equilibrium over here, it's a fixed point. You disturb it a little, you make it go a little this way or this way, but these arrows will ensure that even if you disturb it a little, it'll again go back to this point. So this is a stable attractor fixed point or a stable equilibrium configuration, whatever you want to call it. Now, this is x dot versus x. If the same scenario, if the same system were to be viewed in the x versus t graph, then what would you see? You will see x is equal to AB is this fixed point. Here in the x versus t graph, that x is equal to AB is the horizontal dotted line. That's the limiting value. That's the attractor state. You start with any value of x. Here we are starting from 0, but here I have kept it a little more general and I've called it x naught. X naught could be here also, starting from 0. Anywhere to the right of this, to the left of this black dot, right? You start and you will keep moving. There's nothing that can stop the growth of x, as in here. So this whole march along this functional path is the equivalent of this progression along the horizontal line. X is increasing along this line. Here, x is increasing in t. And eventually, slowly, it will be converging towards this attractor state, x is equal to a by b. That is what it is. If you start with the value of x to the higher side of the black dot, which I have not drawn here, but suppose if I had increased the height of this x-axis and I had drawn the graph here, then this, now you follow something. This is the point that I'm trying to make. Occasionally, it may not be very easy for you to assign initial values and solve integrals and all these things. But in this case, in this xt diagram, I said that the initial value of x as a function of t was t equal to 0, x is equal to 0. Therefore, you start here and then you converge here. But suppose x starts at a non-zero value higher than x equal to ab. Suppose it starts somewhere here. What will be the graph like? You don't even have to plot all that. Just look at this diagram over here and you'll immediately realize that if you start with a higher value of x equal to a by b, this inwardly leftward going arrow, going from right to the left, this leftward going arrow will immediately imply that the graph will be a converging graph like that. It will converge. You don't even have to solve the integral, assign initial conditions and all that. Here, by this very simple approach, you get a very general insight into what will be the behavior of x, what will be the qualitative behavior of x as a function of t. Just by looking at this, you should be able to understand what should be the qualitative behavior of x as a function of t, that x is equal to ab will be the limiting value if you start from the left of the black dot. X, again, it will be the limiting value if you start to the right of the black dot. But if you start to the left of the black dot, x will keep growing as in here. But if you start to the right of the black dot, then x will keep decreasing and converge to a by b, which I have not plotted here, but you should be able to figure that out in your mind. Okay, so this is one demonstration of how, a little simple demonstration of phase plot approach. It gives you good insight. As I said, I mean, you will be ultimately doing a good lot of things computationally. Fine, that is all right. Working things on the computer reduces a good deal of trouble for you. Fine, that is all right. But it should also be helpful if just by a little half a page calculation or something, you are able to figure out that this is the final result that I should expect without going into too much trouble. So that way you'd also be able to have some confidence that your code, your program that has given some result has run successfully as per expectations. Let us now go on to another example. Earlier, I mean, now we have talked about a minus bx, just a hypothetical example. What about a plus bx? I plot this function a plus bx where both a and b are positive quantities. This is the graph x dot versus x, right? And so A and B are positive quantities. So x dot versus x. So when is it that you intersect the horizontal axis? You intersect the horizontal axis when x dot is equal to 0. Therefore, x is equal to minus A by B. Minus A by B is somewhere here to the left of the origin. Now, this is the function, right? Incidentally, these are all linear autonomous functions, first order autonomous. So if fx is the equation of a straight line, then it's a linear autonomous function, and the solution will give you only one root here. Linear equation gives you only a single root. So here x is equal to a by b. Here, if you solve it, x is equal to minus a by b. So only one fixed point. Right. Now let us see. Uh, this inclined line, this straight line, solution a plus bx is above the horizontal axis. If it is above the horizontal axis, then you assign the arrow. For this region, you assign the arrow to the right. Here it is intersecting. It's a fixed point. To the left of it, it has gone below the horizontal line. Therefore, the arrow will now go in the negative direction because x dot is negative in this zone. Here, to the right of this circle, x dot is positive. Arrow is going to the right. X is increasing. Here, to the left of the circle, x dot is negative. So arrow is going to the left. It is decreasing. Okay. Now you notice something. I've written two words here. Fixed point, it is all right. But I've written the opposite of what I wrote over here. Stable, now here unstable. Here it was an attractor. Here it is a repeller. Repeller is something that pushes away. Why am I saying pushes away? Because you can see that the arrows are coming out of this circle, right? Things are not going inward. So this is like you're balancing a pencil on top on its tip. It is vertically standing upright, but a little bit of disturbance. If I push this thing a little this way or this way, it will not regain its original equilibrium configuration, but rather it will move far away from it. And so it is that these arrows are indicating that a little disturbance this way or that, and the arrows will ensure that you will not regain the uh, equilibrium that you had. Okay. There is also a slight difference of the diagrammatic approach. If it's an attractor, you make it a black circle. And if it's a repeller, you do not fill in the circle, you just leave it white as it is. Why? Because this means that things are going in and filling up this circular zone, so that's why it is black. There's just a convention, nothing else. And here, it is as if things are draining out of this circular region, things are moving out, and it's emptiness inside. So that is why repellers are drawn by white circle and the attractors are drawn by a black dot. So just to indicate what they are, you don't have to write anything or anything. Just I mean, matter of convention. By looking at it, you'll if you just were to draw a black dot, you'll immediately be implying that this is a stable attractor fixed point. But of course, the arrows also would show the same thing: a black dot with flanked by two inward turning arrows, a white circle flanked by two outward directed arrows. So I hope I have been able to make you understand clearly with the help of two very basic linear equations, the phase plot approach of first order autonomous systems. Now I shall just take two or three slightly complicated nonlinear examples. One of them we have already studied, which is the logistic equation A x minus b x squared. This is a square order. Okay, let us first plot this diagram. And so this is something that we have already done in finding the integral solutions. So here it is no longer a linear equation, it is a nonlinear equation of the quadratic order, that is to say second order. Therefore, you immediately realize that you should get two fixed points when you write x dot is equal to 0. X dot equal to 0. What are the two fixed points? One is at x equal to 0 and the other, I mean, ax minus bx squared is equal to 0. A and b are, of course, positive once again. And you have x equal to 0 and the other fixed point is x equal to a by b. Okay. We are plotting x dot versus x. There are many things written over here. Let us slowly follow, have a clear idea of what these are like. x dot equal to, sorry, x is equal to 0 is uh, an equilibrium point or a fixed point here. X is equal to a by b is a fixed point here. This is the equation of a parabola. Initially, when x is equal to small, you can neglect the bx squared, and your early growth will be almost like a straight line. But then gradually, the minus bx squared term starts asserting itself. And so, and with the minus sign, there will be a break to the growth of x. So x dot will eventually reach a peak value, and then it will start falling down. What are the values pertaining to the peak? What is the condition for the peak? At the peak, basically we are plotting x dot versus x, or rather, I mean, equally, since x dot is equal to fx, you are plotting fx versus x, right? So at the peak, f prime x is equal to 0. Okay, so we shall now find the condition pertaining to that. If f prime x is equal to 0, fx is equal to this thing, if f prime x is equal to 0, then you'll have a, take the derivative, f prime meaning derivative of f with respect to x, not t. Be careful. df dx, f prime is df dx. So df dx is equal to 0, take the derivative, you have a minus 2bx is equal to 0. Therefore, x is equal to a by b by 2. Okay, you define a by b as k. Okay, so k, so this thing will be peaking. So if you have a fixed point at x equal to 0 and another fixed point at x is equal to k or a by b, then this function will peak somewhere. Function will peak at x is equal to a by b by 2. Okay, fine. Sorry, just a minute. Okay, so the function will peak at a by b by 2 or k by 2. So here is the function peaking at this value. See, this is a parabolic function. This is whatever you have, the area under the curve to the left of this vertical dotted line is equal to the area under the curve to the right of this vertical dotted line. So there is a perfect symmetry. Okay, now let us look at the implication of this parabolic function. Above this line, so this is the horizontal line, this parabolic function is above this line. So in this region, x dot is positive. If the function is above the horizontal line, wherever the function is above the horizontal line, x on the vertical, sorry, on the horizontal line, you will assign a right going arrow. So here it is above the horizontal line, so you have assigned a right going arrow. Beyond this point, the function is slowly going, is going below the horizontal line. So you can see beyond the black dot, it is going below the horizontal line. So x dot is negative to the right of this black dot. So you assign a left going arrow. So immediately you realize that to the left of this black dot, this arrow is going towards it. To the right of the black dot, this arrow is going towards it. So this is a stable attractor state. What about this thing? It is unstable. Why is it unstable? Because immediately you don't even have to plot anything on the other side. Of course, on the other side, it will again go below the horizontal line. This function will go below the horizontal line. But you can see that an arrow is coming out, which means that it is an unstable repeller. Okay, so you start anywhere between this white circle and the black dot, you will keep going to the right. And you start anywhere to the right of the black dot, you'll keep going to the left. So this will be unstable. Things will move out from here and go towards here. Attractor, it is stable. Okay, there's also something else for you to understand. One is that starting from here, anywhere here up to this point of x equal to a by b by 2, up to this point of this vertical dotted line, here you have growth at an increasing rate. And here you have growth at a decreasing rate, growth of x. How so? Just see, what is it? Let us now refer to our logistic equation. This is the logistic equation, the diagram of the logistic equation. If you you have got the notes, you can refer to those notes. You start with an initial value of x naught. If you look at this function, x dot equal to ax minus bx squared, I told you that you will not be able to start, you should not be, you have to choose your initial condition judiciously. So if you say at t equal to 0, x is equal to 0, this will vanish and this will vanish and x dot equal to 0. If x dot equal to 0 at x is equal to 0, then nothing will grow thereafter. So you actually have to start at a non-zero initial value of x, which I'm calling x naught. So this is the x naught. Here, this is that x naught. After which, the function will keep growing at an increasing rate up to this point. Just check the notes on logistic equation. You have them. Up to this point, you have. So at this point, it is k by 2. I've written a comment over here. This point is the same as f prime is equal to x, f prime x is equal to 0 in the x dot plot. So basically, you start from here, you go up to here at an increasing rate. The equivalent of that in the x dot versus x diagram is this path. Along this path, you have growth at an increasing rate. This is what you mean. Here you have growth at an increasing rate. You're growing, but it's concave upwards. Hence, it is growth at an increasing rate. Then beyond this point, you will grow all right, but this is because of nonlinearity. The growth will be at a decreasing rate. So from here all the way towards the attractor, which is A by B, you will keep growing at a decreasing rate. And that scenario is reflected in this diagram, that from here, this point is here, this thing. This point is the same as f prime x is equal to 0 in the x dot plot. So from here to here, as you grow, you're growing at a decreasing rate. That is reflected in this diagram by this curve. You're growing at a decreasing rate. And then eventually, you'll be attracted towards k equal to a by b. This is what it is. If you had started above k by 2, if your initial condition were not to have been here but here, you would have always grown at a decreasing rate. In this diagram, it would have meant that you would have started somewhere to the right of this vertical dotted line, and then you would have converged to this point. Now, I did not discuss in the class what would have happened if you had started at a value of, if your initial condition was greater than k equal to a by b. That I did not discuss in the class, but you can immediately make out just by looking at this part that if you had started at an initial condition of x greater than a by b, then you will converge to a by b. So this is going to be the rough qualitative behavior. You start at a value of x greater than a by b. There is a convergence attractor towards this thing. So this I did not discuss in the class. It would have been difficult. There would have been mathematical complications in working on that out. But just by this little simple diagram over here, you will immediately be able to figure out what will be the general nature of the function, the broad qualitative nature of the function, if its initial condition, if the initial condition of this dynamics were to be greater than the limiting attractor value. So that is what it is. This is the logistic equation, ax minus bx squared. We also discussed a problem only in the last class of a particle falling through a long column of air, parachutist or whatever. That's kind of an equation is, I hope you recall the equation. A dv dt is equal to g minus kv squared by m. G would be like your a over here and k by m would have been like your b. So particle falling through a long air column, that's this equation. Incidentally, particle falling through a long liquid column is this equation. So all of these dynamics that I have discussed will pertain to that thing. So particle falling through a long air column. This is the general equation that you work with. Again, a and b are positive quantities. And sorry, just a minute, please. Yeah, a and b are positive quantities. And so let us now try to plot this function. Again, it's actually this, if you think about it closely, x dot equal to ax minus bx squared and x dot is equal to a minus bx squared are really the same equation. But there is a slight shifting of the origin here. Earlier, you had x equal to 0 here as one fixed point and x equal to a by b here as the second fixed point. So if the vertical axis x dot were to be shifted and made to coincide with this vertical dotted line by a transformation of coordinates, then it would have been like this. That is all there is to it. So really there is not much of a difference between this equation and this equation. Anyway, so let us now see what are the dynamic quantities? I mean, what are the fixed points? X dot equal to 0. X dot equal to 0, you have x is equal to plus minus square root of a by b. Okay, these are the two fixed points. So one fixed point will be minus square root of a by b, another fixed point will be plus square root of a by b. Okay, when x is equal to 0, x dot is equal to a. So this is the point where you have this thing, x equal to 0, x dot equal to a. So this is again a parabolic path. This function is above the horizontal axis in this region, going from the empty circle to the black circle. So above this, so in this region, you assign a right-going arrow. But then beyond this black dot, the function is falling below the horizontal axis. So you assign a left-going arrow here. Immediately you will realize that this is a stable fixed point. And here, if this is going to the right and this function has fallen below, so here x dot is negative, this is going to the left, this is an unstable fixed point. Incidentally, I've written a comment over here which I should stress upon. Alternate fixed points are opposite type. What do I mean by that? See here in the first two examples, a minus bx and a plus bx, there was no issue of an alternate fixed point. Why not? Because there was only one fixed point. You're solving a linear equation, right? As equation of a straight line. X dot as a function of x is just a straight line, just one root. But here you have two roots. Here also you have got two roots. And then you can have multiple roots. Depending, you have a cubic equation, you can have three roots. I give you x dot equal to sine x. If you have sine x, then you'll have infinite number of roots because it will just keep going up and down and it will have infinite number of intersections of the horizontal line. So infinite number of roots. But try to understand this one point clearly, that whatever it is, alternate fixed points must be of the opposite type. So if this is unstable, then the one to the right of it must be stable. Because if things are coming out of this fixed point, then they have to approach the next fixed point. So this point, if it is repelling, then this point must be attracting. And so it is, you have the same scenario over here. This point is repelling, then the immediate point, immediate to the right of it is an attracting point. Suppose I had a cubic equation and there was another point to the left of this thing. That would have been attracting because the arrow would have headed towards that. Arrow coming towards a fixed point is an attractor. Arrow going away from a fixed point is a repeller, an unstable repeller. And the former is a stable attractor. And you can't have two repellers side by side, because if you have two repellers side by side, where will the arrow go to as it comes out of one repeller? Or if you have two attractors side by side, how can you have two attractors side by side? Where, I mean, from where, I mean, where will be the two arrows going to at the same time? So it must be repel one, go from one to the other. From the from part will be the repeller part, the to part will be the attractor part. So that is what it is. And here at this point, f prime x is equal to 0. Again, x dot versus x, meaning basically you're solving fx as a function of x. So here f prime x is equal to 0 again. If that is so, so let us see what its value will be. I mean, f prime x is equal to 0, that will coincide with x equal to 0. This is the peak. Okay, now let us see. Here, it is the function basically you start at x equal to 0. Look at this function. At t equal to 0, if I set x is equal to 0, x dot will still be equal to a, meaning that x will still be able to grow, even if you start with nothing. So if you say that you're starting at x equal to 0, this is basically growth at a decreasing rate all the time. So here, you start at x equal to 0, you go up linearly for a little while, and then, I mean, almost linearly, not exactly linearly, almost linearly for a little while, and then you saturate at the stable fixed point. This is square root of a by b, this point. So it is basically like you're starting from here, x equal to 0, and then you're slowly converging towards this point a by b square rooted over. So here in the xt graph, this is the equivalent of that statement. So this is x dot versus x, and this is x versus t. Okay, I've again mentioned this thing that second degree nonlinearity gives two fixed points. This is a second degree of nonlinearity. Again, this is a second degree of nonlinearity. You get two fixed points. And this is a linear equation with these two are linear equations, so you just get one fixed point. Just to reverse the scenario here for the logistic equation, we had ax minus bx squared. Suppose I multiply the right-hand side with -1 and give you a new function, x dot equal to minus ax plus bx squared, right? So that is what it is. Um, I'm not asking you to solve this function or anything. By now, you should gain enough idea of what it is going to be like. You already have this diagram. Now, first you draw the plot, the phase diagram, that is x dot versus x, and you should be able to figure out for yourself what will be the actual integral solution like, even without having to integrate it. Let us see. A and B are positive quantities. Okay, I'm solving x dot equal to 0 just to find the fixed points. As before, x is equal to 0 is a fixed point and x equal to a by b is a fixed point. But now we have a minus sign, net minus sign on the right-hand side. If I plot this function, initially x is a small quantity, so I can neglect the bx squared. So initially I'd be solving x dot is equal to minus ax. So that is this function, almost like a straight line initially for small values of x. But then, so minus ax means it is going down, x dot, and this is x. So minus ax means that it is slowly going down. If it is going down, but then as x keeps going down, x squared will be a positive number that will keep growing with a plus sign. So eventually it will make this plus sign will assert itself, and eventually it will make the function turn and start growing up again for large values of x. Okay. All the previous discussion held. This basically what you're doing is just that you're reversing this, flipping this function above the horizontal line to this function below the horizontal line. That is all there is to it, nothing else. And so at this, in this region, since the function has fallen below the horizontal line, x dot being negative over here, you assign a left going arrow between these two. Immediately the right fixed point to the fixed point to the right will become an unstable repeller. Arrows will be coming out of this fixed point, and they will be converging towards the first fixed point here. So this will become a stable attractor, this will become an unstable repeller. And now suppose if I ask you, you are starting somewhere between this black dot and this, you are starting somewhere between this white circle and this vertical dotted line. So let's say you have started somewhere here. The vertical dotted line corresponds to a by b by 2, as in here. You have started somewhere here. So this will be the resulting graph. This point corresponds to the minimum in the x dot plot. So here, this is this thing. You start with a high enough value. You will initially decrease at a decreasing rate like this, concave down, and then it will decrease at an increasing rate like this, concave up. So this point corresponds to this horizontal dotted line, and a by b, the unstable fixed point, corresponds to this horizontal continuous line, a by b. You have started from somewhere here, you are falling down and going this way. This function, although I mean, maybe later I can discuss this thing, this function has got some serious importance in physics, a function of this form. In statistical physics, in a large aggregate system, there are various particles, like I have discussed. A gas system is made up of many particles and they are all moving around very rapidly. But gases are charge neutral particles. But suppose I give you a gas of electrons. Where do you get a gas of electrons? Inside a metal crystal lattice. In a metal crystal lattice, the metal ions form a bond, and in the process, they release electrons. So good conductors have these free electrons moving around, such as copper. And these electrons almost are free to remain within the body of the conductor and move around, or go wherever they want, but not free enough to move out of the conductor. That is to say, start vaporizing. So these electrons form a gas cloud within the conductor, and these free electrons conduct a current. The behavior of the free electrons is given by the Fermi-Dirac equation, whose form is somewhat like, whose form is the integral solution of an equation that is somewhat like this: x dot equal to minus ax plus b squared, bx squared. If you integrate this equation, the resulting solution that you will get has got a family resemblance to the Fermi-Dirac distribution of an electron gas in a metallic conductor. A family resemblance. There you plot the number of particles containing a certain amount of energy, epsilon or whatever, and so that sort of an equation corresponds to this plot that I have drawn over here, and I've written a comment here. This is just the inversion of the logistic equation. So I hope you have understood this whole discussion of phase diagrams. Phase diagrams are quite useful tools. They will help you avoid uh, seriously integrating something, an equation that you have been given, and then finding its integral solution. Even without that, you can gain much insight into the general nature of the integral solution. So here, in fact, I've drawn the integral solution without having integrated it. Here also, I drew the integral solution here for x greater than k by k equal to a by b. If you start with an initial value that, what will be the general nature of the integral solution? So as you can see, these are very simple tools to work with. I will just expand the discussion a little. So far, we have just drawn a good whole lot of diagrams and all that stuff. Right. I mean, maybe we have made a geometric understanding, a geometric approach to the problem, this whole business. But there is also an alternative way of finding the stability of fixed points. We have drawn diagrams, then we have determined with the help of a diagram which fixed point is stable and which fixed point is unstable. But the question is that this can be done in another way also. You may not be very geometrically or diagrammatically minded. So how will you do that? There's again a very simple way of doing it without getting into all this diagram business, although that you can do both and the one will confirm the other, verify the other, support the other. So let us see what you get. How will you find the stability of fixed points if you don't have to draw a diagram? So what is the requirement of a fixed point? A fixed point is when x dot is equal to 0. So you have been given an autonomous system, x dot equal to fx, and the fixed point condition is x dot equal to 0. So f of x at at x subscript c is x subscript c is the fixed point coordinate. So as soon as you solve this equation, x subscript c is the fixed point. So there is here x subscript c is a by b. Here it is minus a by b. Here you have two such points, 0 and a by b. Here you have got square root of plus minus a by b. So x subscript c is like that. Now, how will you determine the stability of fixed points? Suppose the function, autonomous function fx can also be complicated. So maybe you will not be able to draw by hand. Incidentally, you can also draw one of the later lab assignment sheets that I will give you will be to plot all the autonomous functions that you had earlier. You had all the autonomous functions, Euler's method and all that. So one lab assignment will be to just plot x dot versus x to see what those functions are like. So, okay, but sometimes you may not be able to draw, you may not be able to have a computer at hand, or you may not be, the function is so complicated that you can't draw the graph of fx as a function of x by hand. Even so, there are ways of finding out the fixed points. The fixed points could be found by solving this equation, f of xc is equal to 0. Now, what is the nature of the fixed point? Is there a non-diagrammatic approach to it? Yes, there is. Let us see. Now, you perturb about the fixed point. Xc is the fixed point. You just shift it by a small amount, epsilon. Suppose here we have, this is the fixed point a by b. I just shift it to the right or the left by a very small amount, epsilon. How small? So that epsilon is very much less than x by c, right? So, I'm sorry, very much less than xc. So here is xc. xc is this length a by b. I just shift it by a small amount epsilon either this way or this way. Epsilon by xc is very much less than 1. It's at absolute value at least. Okay, so epsilon is very much less than xc. Now, if you look at this equation, xc is a fixed point. So x dot at xc will be equal to 0, right? This fixed point is only the outcome of x dot equal to 0. So at x subscript c, x dot is equal to 0. So if I take this equation and take a time derivative of this equation, you'll get x dot is equal to xc dot plus epsilon dot. But xc dot is equal to 0, so x dot is equal to epsilon dot. And that is equal to, so x dot is equal to fx, right? That is what you start with. X dot is equal to fx, but then x dot is also about the fixed point, x dot is also equal to epsilon dot. Okay, epsilon dot is equal to fx. And what is x? X is equal to xc plus epsilon. So epsilon dot is equal to f of xc plus epsilon that has been written over here. Now what we will do is that we will do a Taylor expansion of this equation, which is not a very difficult thing to do. Epsilon dot is equal to fxc plus f prime xc epsilon plus 1 by factorial to f double prime xc epsilon squared plus etc. It keeps going on. Now, slowly you try to understand this thing and carefully. In this Taylor expansion, fxc is equal to 0. That is the requirement that that is when you have x dot equal to 0, f of xc is equal to 0. So fxc is equal to 0. And epsilon is a very small quantity, much smaller than xc. So if epsilon is a small quantity, we can neglect terms with epsilon squared and higher. This has been stressed upon many times in the class for you, that if a number is small, then its higher powers can be neglected against the lower powers. Okay, if that is so, then you are just left with epsilon dot is equal to f prime xc into epsilon. That is what it is. This is an approximate equation, but this equation is a linear equation. You can just see that it is just like x dot is equal to some constant into x. What is the constant? The constant is the derivative of x, derivative of f with respect to x at xc. So you neglect the epsilon squared term, and then you get a linear equation. Epsilon dot is this thing is 0, this thing is neglected, even anything higher than that is also neglected, and so you are left with epsilon dot is equal to f prime xc into epsilon. Now you are writing this thing as d epsilon dt is equal to f prime xc into epsilon. D epsilon by epsilon, this is dt, so the t is looking, oh God. Now you have this situation, d epsilon dt, this is t and this is epsilon. So just be a little careful about that. I've written this thing more explicitly or more clearly here. D epsilon by epsilon, separation of variables, this epsilon goes to the left hand side, d epsilon by epsilon is equal to f prime xc into dt. Okay, integral left hand side log epsilon is equal to integral constant log a plus f prime xc. F prime xc, be clear in understanding that this is a constant quantity. It is the derivative of f with respect to x at the fixed point value xc. That derivative will not be 0. fxc may be equal to 0, but the derivative of f is not equal to 0. Also, be clear in understanding that at this point f is 0. Fx is equal to 0. But you can see if the derivative were to be 0, then this line should have been horizontal, but it is not. It has got a slope here, non-zero slope. Similarly here, fx is equal to 0, but this function has a non-zero slope here as well. And likewise here also non-zero slope and non-zero slope with respect to x, f as a function of x. Okay, so so this thing is a constant quantity, non-zero constant quantity derivative. It comes out of the integral, and so you just integrate integral delta t, dt with t. After that, you put take the anti-log of it. Epsilon is equal to a into e raised to f prime xc into t. Okay, and what is epsilon? Epsilon is equal to x minus xc. Why? because x is equal to xc plus epsilon. Therefore, epsilon is equal to x minus xc. Hence, I put this thing over here. X is equal to xc plus a e raised to f prime xc into t. Okay. Now, follow very carefully. What is the requirement for stability? You see this thing here? This whole thing is epsilon. Epsilon is the little disturbance that you have created about xc, right? X is equal to xc plus epsilon. So this whole thing is epsilon, and it has got a dependence on time. If a system is in stable equilibrium, such as a flat pencil lying flat on its side, then if you say xc is its stable configuration, you add a disturbance to it by, let us say, lifting one end and then releasing it. That disturbance will go to zero. Real, okay. Now, what is the requires? It should go to zero as time increases. Now, what is the condition for this thing to go to zero as time increases? That is to say, for xc to be a stable fixed point. The condition is that as t goes to infinity, x will go to xc. That has been written over here. Now, this will happen only when, follow carefully, f prime xc is a negative quantity. E raised to a negative number multiplied by infinity will go to zero. As t goes to infinity, if this thing is negative, minus something into infinity will make this thing e raised to minus infinity. That thing will go to zero. So this will only happen when f prime xc is a negative quantity. That is the condition of stability. Otherwise, this thing will be unstable, meaning that as t increases, e raised to whole thing shall go to larger and larger values. That is, you are moving far away from the original equilibrium. And if that is so, that can only happen when f prime xc is a positive quantity. So, if you are given an autonomous equation x dot equal to fx, standard approaches to these problems is, follow carefully now, don't have to do anything. Just two things you have to do, and they all are things that you've learned in your class 10 or 11 when you started learning calculus 11, I think. Yes. X dot equal to fx. First question, find the fixed points. What will you do? Fx is equal to 0 or x dot equal to 0. You solve the function fx is equal to 0, you get the number of fixed points. If it's, let's say, a linear equation, one fixed point, quadratic equation, two fixed points, any other thing, whatever it is, you'll get those many number of fixed points. So you'll get some number of fixed points. Next question is that identify whether a fixed point is stable or not. What will you do? You will fit in take the derivative of f with respect to x, put the value of the fixed point in that derivative function and see whether the derivative is coming out to be positive or negative. If it is negative, it's a stable fixed point. If it is positive, if the derivative of f prime xc, this is the derivative. If it's positive, it is an unstable fixed point. Positive meaning greater than 0. If it's negative, it's a stable fixed point. So that's a very simple way of working with these problems. Let us just see. I've written two comments over here: non-oscillatory convergence and non-oscillatory convergence. What do I mean non-oscillatory? Oscillatory meaning, just think of a pendulum. The equilibrium point of a pendulum, I mean, if you don't disturb a pendulum will remain suspended along the vertical axis. You disturb the pendulum a little, going either to the left or to the right, it'll keep oscillating, and then eventually it will converge to, the oscillations will die out, and again it will retain its original equilibrium configuration. Okay, by the way, the pendulum's extreme ends are also fixed points, right? That is the point where velocity goes to 0, etc. All those things are happening, but they are unstable fixed points. At the extreme end, momentarily it stops, and then it starts coming down again and doesn't go back. I mean, doesn't go back before the start of the next cycle, that is. But the equilibrium point vertically, along the vertical direction, along the line of suspension of the pendulum, uh, is a stable equilibrium point. And that equilibrium is an oscillatory. I mean, I mean, if you disturb the pendulum about that equilibrium, it will oscillate and eventually converge to that equilibrium configuration. But here, the equilibrium is non-oscillatory. Why is it non-oscillatory? Just let us return to this diagram. If I disturb any of these fixed points, let's say this is a stable equilibrium, right? I disturb it a little. The arrow is flipping to the left. So if I start at a point slightly to the right of this black dot, in time it will take slowly to converge, but it will take infinite time. Be extremely attentive on this point. It will take infinite time to reach this point. And if it takes infinite time to reach this point, then it will not overshoot and go to the other side, as happens in the case of a pendulum. Therefore, this kind of a convergence is not an oscillatory convergence, as you see in the case of a pendulum. This is a non-oscillatory convergence. What do I mean by saying that if it takes infinite time? You can see it in this equation itself, that x will go to xc only when an infinite amount of time has elapsed. So this is not an oscillatory convergence. It's not going to keep shifting to the left and the right of the equilibrium point and eventually converge. It will take infinite amount of time to converge to that. So hence it is a non-oscillatory convergence. What makes a pendulum have an oscillatory convergence and this thing have a non-oscillatory convergence? Short answer, that these are all first order equations. First order equations do not accommodate oscillatory convergence. A pendulum is governed by a second order equation. I hope you are aware of that fact. M d2x dt squared, or M d2 theta dt squared, d2 theta dt squared, x double dot or theta double dot, that kind of a scenario. But here it is x dot. I'll discuss these things later, but just in case you were wondering that why should a pendulum have oscillatory convergence and this thing doesn't have an oscillatory convergence, it is because it is a first order equation. To have a second order, to have oscillatory kind of a convergence, a second order equation is a must. We'll discuss all these things when we go to second order systems later. But anyway, for the time being, I hope you have understood this sort of a situation. There is something else I'd just like to stress upon. Occasionally, you may be in a spot of trouble. What is the spot of trouble? The spot of trouble is that for a fixed point, fxc is equal to 0. But then f prime xc may also be equal to 0. I hope you appreciate that point. Here, f prime xc is not equal to 0. Here, f prime. What is f prime? F prime is the slope of the function f. Function f is equal to x dot. The slope is non-zero here, non-zero here, non-zero here, non-zero here. But suppose you have a situation whereby, let us say this curve here is touching this line. Then f prime x is also equal to 0, as well as fx is also equal to 0. Suppose I pull this thing down in some way. Then this point will go down, this point will go down, this function will eventually come down, and just this thing, this horizontal line will just tangentially touch the peak of this function, right? Suppose that thing were to happen. Then at this point, both fx is equal to 0 as well as f prime x is equal to 0. So how will you solve that sort of, how will you handle that sort of a situation? Well, there is no immediate prescribed, I mean, that sort of a point is neither a stable point nor an unstable point. When you say f prime x is equal to 0, and you say, what do you mean by neither a stable point nor an unstable point? Let us just see how it happens. Let's take this fourth example, a minus bx squared. I'm pulling this thing down. If this thing is pulling down, eventually this point over here is going towards this axis, right? By pulling this thing down, meaning that I'm reducing the value of a. When x is equal to 0, x dot is equal to a. Okay. So when a goes to 0, x dot will become minus bx squared. So that will be a parabola, exactly the same shape, except that its peak will coincide with the origin. What will happen to this white circle and this black dot? As you're pulling this thing down, the black dot will keep moving to the left and the white circle will keep moving to the right. And at this point, when the horizontal axis is just tangential to the peak, the black dot and the white circle will both collide. And once they collide, one is stable and the other is unstable. At this particular point, when both of them collide, you cannot say that it's either stable or unstable. That is the conclusion. So you don't have to work these things out algebraically, solving integrals and all that. Just by looking at the diagram and running a simulation in your mind. What is the simulation? What will I see this whole thing to be if a were to gradually made to go to 0? This whole function will start slowly subsiding down, sinking down. And there will come a stage when this will move to the right, this will move to the left, and this point will come here, and all three of them will coincide here. Right? And when all three of them coincide here, you will have neither an unstable fixed point nor a stable fixed point. So it is technically, just a minute, I'm sorry. Hello? I'm taking a class, I'll call you back later. Okay. Everybody thinks that I must be the foreign minister, so I can have a solution of the Ukraine crisis. That's why I'm getting so many calls this morning. Yeah, that is what it is like. Okay. So now, what happens when both f vanishes and f prime vanishes? Follow this discussion a little carefully. This has got a huge importance in physics. Not that I'll ask you to worry too much about that in your course, but it has got a huge importance in physics. It is known as a critical condition. In the critical condition, both f and f prime vanish. If that happens, then epsilon dot is equal to fxc plus f prime xc epsilon plus this whole thing, etc. Now fxc is vanishing as before. Now, in addition to that, f prime xc is also vanishing. Both of them vanish, in which case you can no longer neglect the epsilon squared term. Epsilon dot will be equal to some constant into epsilon squared. That is what it is. In which the epsilon squared term can no longer be neglected. It will be a very small number, but it will still be some number, whereas the first two have gone to 0. So you can't neglect a small number against 0. I hope you know, you're understanding what I'm driving at. Right, so 0 is 0, absolute smallness, infinite smallness, if you like. So basically now you have to work with the second order term, the epsilon squared. Let us see what you will get. D epsilon dt on the left hand side is equal to some constant into epsilon squared. Next, you will just do the variable separation. Epsilon raised to minus 2 d epsilon is equal to f prime xc by factorial 2 is 2 dt. So you integrate this thing, epsilon raised to minus 2 d epsilon will be epsilon raised to minus 1 by minus 1. And this thing will be f prime xc by 2. Now you see this thing, t minus a. A is an integration constant. And so epsilon will be equal to this minus, so this is 1 upon epsilon actually, and this is a minus sign. Minus sign I'm taking to the right. Epsilon is equal to x minus xc. So x is equal to xc minus 2 by f double prime xc into t minus 1. As you can see here, as t goes to infinity, x will also go to xc. This will also show you stability. Fine, that is all right. As t goes to infinity, x goes to xc. But this kind of a convergence is known as a power law convergence. It's a slow power law. Power law meaning 1 upon t. So this thing is basically t raised to minus 1, right? So t raised to minus 1 kind of a power, whereas this thing is not a power law kind of a convergence. This is an exponential convergence. This is an exponential convergence if f prime xc is negative. But this thing is a power law convergence. Just appreciate one important thing. You can test it on your computer or whatever later, that an exponential function decays much more rapidly than a power law function. You can just plot y is equal to e raised to minus x and y is equal to 1 upon x. Just you can plot on your computer. You all have laptops at home. Just check for yourselves. You plot both. Y is equal to e raised to minus x and y is equal to 1 upon x. Plot them and see for large values of x. Both will go to 0. When x goes to infinitely large value, both will go to 0, all right. But the fact is that the exponential function will rapidly converge to 0, much more rapidly compared to the power law function. So this will be a slow convergence as in a power law. I just told you that this equation, this thing has got a huge importance in physics because all phase transition phenomena, phase transition meaning ice going to water, or in the electromagnetic theory course, I hope some of you will recall, we discussed ferromagnetic system and paramagnetic system, ferromagnetic phase going to paramagnetic phase, all sorts of things. Whenever you have a phase transition, the behavior of things like, various measurable things, thermodynamic quantities, depend on temperature. That is also T, but here this T is a small t as representing time, as we have implicitly assumed. But there T is capital T as in absolute temperature. So there you have all critical phenomena, phase transition, you have this kind of a slow power law convergence, because whenever there is a phase transition, in these kind of autonomous systems, that are equations that govern systems undergoing phase transition, this first derivative will vanish. So that is what it is. I've given some examples over here as to how you will adopt this approach. So if you don't want to use a diagram, or suppose in the examination question, you have just been asked to identify stability or instability without explicitly mentioning, draw a diagram and all that, etc. You can do it diagrammatically, or you can do it in this way. Let us see what is this thing. Fx is equal to a plus minus bx. F prime x is equal to plus minus b. So you can see that if f prime x is equal to plus b, then unstable, and if f prime x is equal to minus b, then stable. Just some simple examples I've written here. Fx is equal to ax minus bx squared. F prime x is equal to a minus 2bx. So when x is equal to 0, f prime 0 is equal to a. So there are two fixed points here, x equal to 0 and x equal to a by b. So when x is equal to 0, f prime 0 is equal to a, which is the unstable fixed point, as has been drawn here. As you can see that f prime will be positive here. And when x is equal to a by b, f prime a by b is equal to minus a. That is, if we just put x is equal to a by b, so you will have a squared by b minus b. So you put, I'm sorry, here, x, a minus 2bx. So you put a minus 2b into a by b. So a minus of 2a. A minus of 2a will give you minus a, stable. So just see in these diagrams what the slope is like. If it is diving down from the left to the right, it's stable. If it is diving down from the right to the left, it is unstable. Here you can see that it is diving down from the right to the left like that, unstable. If it is diving down from the left to the right, stable. Here also, diving from the left to the right at an incline, stable. Here, unstable. Just check that. The slope, if the slope of the function f is negative here, it's a stable point. If it's positive here, it's an unstable point. Negative here, stable. Positive here, unstable. It's the same thing you can keep doing. Fx is equal to a minus bx squared. F prime x is equal to minus 2bx. So if x is equal to square root of a by b, so if you put square root of a by b, the minus sign still stays like that. So it'll be a negative quantity anyway. You don't even have to work it out. Just see whether it has got a plus sign or a minus sign. Immediately you will say stable. And if x is equal to minus square root of a by b, the minus here and the minus here will make it plus. And so f prime will be a positive quantity, hence unstable. So that's the discussion I wanted to have. We will use this whole discussion later in some problems. Today we have about 5 or 6 minutes left. I'll just show you a few simple things. There was some mistake I made. I'm sorry. In the mathematical theory notes, I'm sorry. Here, I think I made some mistake somewhere over here. I've corrected that mistake just give me a minute. I will show you the correction. here, just a minute. Please just bear with me. Here we were discussing all these notes on these phase plotting, pages 18, 19, 20. In page 19, there were some omissions, not mistakes really, omissions. So I have written that, corrected those things. Fx is equal to minus ax plus bx squared. So some extra points I have just added. So you can just check page 19. This is the mathematical set of mathematical note corrections, right? So I'm teaching this course for the second time. So I hope there aren't too many errors left in the old notes. Okay, so I will just briefly touch upon the bicycle rider in motion bicycle motion against air resistance problem. We just about have 5 minutes left now. And in the next class, we will motivate the physical discussion. So today, I will continue with the physical discussion. Today, I'm just briefly motivating the physical nature of the problem in the little time that is left to us. Okay, so I hope all of you can see this presentation. Can you please just confirm, one of you, quickly? Hello? Okay, okay. Thank you. Thank you. Yes, fine. I'm sorry about this hurried thing. So here, see, we have discussed a whole lot of fluid problems, as in a particle falling through a long air column. Earlier, we had discussed the problem of a particle falling through a long liquid column, liquid air. These are all fluid problems. Here, we are taking up a new problem. This time, not vertical fall, but horizontal motion, let us say. Horizontal motion, as in a bicycle rider riding a bicycle on a road, and of course there will be friction and due to the road on the bicycle rider, the tires of the bicycle, all those things are there, but there is also air resistance. So this problem is physically different from the previous problems we have talked about. In the previous problems, the motion was vertical, falling down under gravity. Here we are not discussing a problem of something falling down under gravity. Something is moving horizontally on the road. But there is air even on the road. So as you are pedaling your bicycle, you will experience air resistance. Okay, so this is a good demonstration of the kind of mathematical applications you can do whatever we have discussed. This is a simple problem otherwise, but it gives you a good test case as to how you can apply various knowledge of mathematical methods to solve this problem computationally. So let us see. So the bicycle motion against air resistance, the equation of the motion is mass into acceleration is a force, right? M is the mass of the bicycle and the rider, both put together. The rider and the bicycle put together have got a total mass M. The bicycle is traveling with a velocity v, and the force is exerted by the rider on the bicycle. So you're pedaling or you're applying some force and overcoming the road friction, overcoming the air resistance, all that thing. But what is that force? In the case of a particle falling under, see, this is also forward motion, but this is in the horizontal direction. In the case of a particle falling under gravity, the force is very easy to write, m into g, right? mg, weight, gravity. Here you have horizontal motion, so F is not given beforehand. So how will you tackle this F business? Let us see. The kinetic energy of the bicycle rider combination is half mv squared, mass into velocity squared by 2. Okay, so we will just have to work with this thing out, applying a slight trick. What we do is that we take the derivative of the kinetic energy. dE dt is equal to m by 2 into 2v dv dt. The 2's cancel, and this is what you have. dE dt is equal to mv dv dt. And so we have got m dv dt. We take the velocity to one side. We write m dv dt is equal to 1 by v dE dt, and that is equal to f, right? M dv dt is equal to f, but dv dt by some trick we have written, f by some trick we have written as 1 by v dE dt. Now, what is dE dt? This is the power output of the rider. See, this is energy. what is it? Where is the kinetic energy coming from? I'll just briefly end on this point. Please just bear with me for a minute. I mean, the bicycle and the rider are traveling with some kinetic energy. So where is this kinetic energy coming from? Energy can neither be created nor destroyed. This energy is coming from the muscular action of the bicycle rider. So the bicycle rider is pedaling and doing work. Work is a form of energy. That energy is transferring itself into the kinetic energy of the bicycle plus rider system. Okay. And work per unit time is also known as power. If it is power, then we write this thing dE dt. E is coming from the work done, right? So kinetic energy is the outcome of the work being done. So this is basically the work done per unit time. So this is the power. And we approximate it as a constant quantity. So m dV dt is equal to dE dt we are writing as P by V, and this m we are taking to the right hand side. So dV dt is equal to P by mv. And this, you notice, is in the form that we have just discussed. dV dt is just a function of V, an autonomous equation. In the next class on Monday, we shall continue. Please just hold on for a minute. I'll stop sharing and I'll just have some instructions to issue. I'll also stop the recording. Just please bear with me. So you are to submit the report of your second lab. I have